Hello and welcome. You should be on page 15 of your Algebra 1 Quarter 3 notebook. In this video, we are going to talk about simplifying radical expressions, specifically square roots. So roots, another way to say that is radicals. And you learned in the past that radical expressions or square roots are really the opposite of squaring a number. So if I have the number expression 1, well, 1 times 1 equals 1 squared, which equals 1. And 2 times 2 equals 2 squared, and that equals 4. And 3 times 3 equals 3 squared, and that equals 9. And I could keep on going all the way up to 15 squared, but I can continue on with variables. What is x times x? Well, in our exponents unit, we learned that when I multiply exponents of the same base, I can add the exponents. So that is 1 plus 1, or x squared. If I want to square x squared times x squared, I would add 2 plus 2, and that would be x to the fourth. X to the third squared would be x to the sixth, and x to the fourth squared would be x to the eighth. Well, our focus is going to be going in this direction. What is the square root of 1? Well, it's the number when multiplied by itself that equals 1. And of course, we know that equals 1. What is the square root of 4? 2. And so on and so on. So let's just kind of look at these nice whole numbers and ask ourselves, what is the square root of 64? Well, it is 8. Now, this is a curious symbol that you might not have seen before, but if you haven't, you're not. It just means plus or minus. That's all it means. And we'll just maintain that plus or minus in our answer. And this will be plus or minus the square root of 196, which is 14. Now, in this case, I have a negative sign outside my square root, so I have to maintain the negative sign. And that equals negative the square root of 225, which is 15. And finally, plus or minus the square root of 81 is 9. So there we go, just some, numbers, taking the square root of numbers that are even. Now, what happens if we add some variables in there? Well, we're going to kind of follow the general same pattern. We're going to find our numeric square root first. The numerical square root. And then you are going to divide your even exponents by 2. Because think about it. If I were to take the square root of x squared, I'd come back to here, x to the power of 1, which is 2 divided by 2. If I were to take the square root of x to the fourth, I would take the square root of this. I would come back to x squared, which is 4 divided by 2. So that is what is happening to my variables with exponents when I do this. So if I look here, I see that I'm going to take the square root of 4, which is 2, and I'm going to divide my 2 by 2 and get 1, or x to the first. So the square root of 4x squared is 2x. In my next example, I have a 9. What is the square root of 9? Well, that's 3. And if I take 4 divided by 2, I get x squared. So the square root of 9x to the fourth is 3x squared. Now in this one, I just have this negative sign out there, so I've got to keep it. And now I don't have any numerical square root, but I do have a 6, a nice even exponent. 6 divided by 2 is 3, so this is negative x cubed. And y divided by 2 is 1, but I know I won't write that one. I will just leave this simplified expression as negative x cubed times y. In my next example, have all even exponents. 12 divided by 2 is 6. 8 divided by 2 is 4, and 20 divided by 2 is 10. And finally, back to having a numerical square root. The square root of 169 is 13. 10 divided by 2 is 5. And 8 divided by 2 is 4. So the nice thing on this page is that I have had within my square roots a number that has a perfect square. What happens when I don't have that? We're going to go on to page 16, and we need to learn a few properties that are going to help us address when we don't have perfect squares. So first is the product property of radicals. If I take the square root of a and I multiply it by the square root of b, that is equivalent to the square root of ab. What does that look like with a number? If I have the square root of 6 times the square root of 8, that will actually equal the square root of 6 times 8, which is 48. The quotient property of radicals says that if I have the square root of a over the square root of b, that equals the square root of a in the numerator over the square root of b in the denominator. With numbers, I would see, using my same 6 and 8, that this would equal the square root of 6 over the square root of 8. These properties become really helpful to me because essentially it's going to allow me to simplify my non-perfect squares. Let's take a look at what that looks like with some examples. If I look for perfect squares, factors of the numbers under the radicals, that is my first step. So I need to look for perfect square factors. So I'm going to have to know how to break down numbers to find perfect square factors. Remember, my perfect square factors are 1, 4, 9, 16, 25, 36, 49, 64, and so on. Then I need to find perfect square variables, and they have even exponents. If I have a variable with an odd exponent, I'm going to have to simplify it. That's a lot of words. Let's see what it looks like in practice. I'm going to take a look at the square root of 8. Well, I know that 8 is not a perfect square, but I know that 8 can be broken down into the following. So I'm going to kind of almost take this backwards. This actually equals the square root of 4 times 2, because 8 is 4 times 2. If I were to separate that out, I'd have the square root of 4 times the square root of 2. We know that the square root of 4, it's a perfect square, that equals 2. And I cannot find the square root of 2, that's an irrational number. So this is my simplified expression, 2 square roots of 2. Now, when you have a number like 8, and you can easily break it down to 4 times 2, it's very nice. But sometimes you have a bigger number, like 108. There are a couple different ways I can show you how to do this. So kind of take a deep breath. Here we go. The first thing is you can kind of say, hey, I'm going to break this number down. I've got that number 108. And, maybe it's divisible. Let me just take my smallest square root aside from 1, but 4. Is 108 divisible by 4? And indeed it is. It's divisible by 4. Apparently 4 times 27 is 108. So I know that 4 times 27 equals 108. Now I also know I can break down 27 into another perfect square. I can have the square root of 4 times 9 times 3, right? Because 9 times 3 is 27. And I've done all of this by just, dividing by 4 because I figured that would work, maybe. Well, now this equals the square root of 4 times the square root of 9 times the square root of 3. I know that the square root of 4 is 2. I'm going to multiply that by the square root of 9, which is 3. And the square root of 3 is a rational number. It will stay. 2 times 3 is 6. So my simplified answer is 6 square roots of 3. I might have also seen, so there is one strategy, that 108 is actually also divisible by 36. It goes in there 3 times. So I could have broken 108 down. Oops, excuse me, I was writing 108 again. which is 36 times 3. That, of course, is the square root of 36 times the square root of 3, which is 6 square roots of 3. Whichever way you do it, you're going to come up with the same answer. But, it's nice to know that there are different approaches. I'm going to teach you one more thing that if this is also, I can also do what I'm going to call a birthday cake method. I'm going to take my 108 and I'm going to put it at the bottom layer of my cake. And then I'm going to try to divide it by the smallest prime numbers I can. So think 2, 3, 5, 7, small prime numbers. Well, this is an even number. I know it's divisible by 2. My calculator, 108 divided by 2 is 54. I know that's divisible by 2. That's 27. Now 27 is not divisible by 2, but I'm going to go to another small. 27 is divisible by 3. That's my next small prime number. And that goes in 9 times. And 9 is divisible by 3. And that goes in 3 times. Building a nice big cake here. And 3 is divisible by 3, and it only goes in 1 time. Now here is where I know I'm done, because look, I've got a candle at the top of my cake. And I've broken it down into small factors. So I'm going to take my factors, I'm going to just do this as another line for another strategy, and I'm going to find twins because I'm looking for square roots. I've got a set of 2s and a set of 3s. These are going to live outside the square root. So I have 2 times 3, and this singleton right here will remain in the square root. And lo and behold, that also equals 6 square roots of 3. So again, it's nice to have variety, so there are 3 different approaches we could have gotten to our same answer. When I look down here at my number 3, well, 45 is a much more simple number to break down into a perfect square because I know 45 is divisible by 5. 5 times 9, and 9 is a perfect square. So I can break this down into 9 times 5. And I'll just leave my exponent there for a second. I'll bring out the 3, so it's 3 square roots of 5x to the 5th. How can I break down x to the 5th now? I need an even exponent. Again, I'm going to take my idea that I can add exponents with common bases and go backwards. I know that x to the 4th times x to the 1st will equal x to the 5th. So I'm going to take out that 4th. This is going to be 3, 5, x to the 4th, x to the 1st. And I will take this out by dividing by 2. And I will get 3x squared, 5x. And that is the simplified expression there. So let's take a look and see how we would simplify this next one. 242 looks like a big number. I might start with a cake. Let's see. 242. It's divisible by 2, so I'm definitely going to divide it by 2 first. And I get 121. The reason I'm very excited by that is a perfect square in itself, right? 11 divided by 11, 11. And here's my birthday candle. So the only twin I have here is an 11, which will come outside the square root, and 2 will remain in. And now I'm left with a to the 9th. Well, I know a to the 9th equals a to the 8th times a to the 1st. B squared is already even, and c to the 0 power equals 1. So that's going to cross off. So I'm going to put a to the 8th times a times b squared, and I've gotten rid of c. So I'm going to divide this here, and I get 11 a to the 4th. 8 divided by 4 is 2. And I get, oops, I forgot my b. Excuse me. 2 divided by 2 is 1. And that is the square root of 2a. And so my final answer on this page is 11 a to the 4th b square roots of 2a. That's all for this video. Thanks so much.